Hi, everybody, and thanks for staying here until the very last talk. I will try to make it as dynamic as possible. Yes, Matthias has said, I'm going to present analog quantum computing for HEP simulations. But I have to say, when I submitted the abstract, so I only have myself to blame, but when I was building this talk, I realized I was facing sort of a min-max problem, in the sense that I'm a particle physicist by training, and we tend to use a lot of jargon, so I'm trying to reduce that to the minimum. If I fail, which I will probably do, let's be honest, please ask whatever is not clear from the slides. And I have one very clear goal in mind before I head back to Valencia, other than the train not being super delayed, and that is discussion. Because I will present to you the challenge that we have, and I will motivate it, and it really is an important challenge that as particle physicists have been discussing and banging our heads against for a long time, and I really hope that the experts of quantum computing, analog quantum computing, can really sit together with us and help us deal with this. Okay, so first acronym that I need to introduce, and hopefully not many more to come, is HEP. This is high energy physics. So this is meant in the broader sense. Think neutrino experiments, particle colliders, but because we work in LHC-based experiments that Miranda already introduced to you, of course, for most of the talk, I'm going to be focusing on the LHC collider, where two protons collide at 4 collision points. But actually, it doesn't really matter that much, because for the sake of the computational tasks that I want to introduce today, it can really be easily applied elsewhere. Like, we all suffer from the same problem. This is really not native to LHC. And here it is. We have a community of QC for HEP, which is quantum computing for high energy physics. We are not very original in acronyms. And the way this community is shaped is we have 2 parts. We have the theorists and the experimentalists. And this kind of drives the way we see the problems. So this is a very nice depiction of all the tasks that we try to achieve. We try to find applications of quantum computing in high energy physics, analog or digital. And you can find the link here, a nice summary. But I just want you to see that there is a very clear separation between theorists and experimentalists in particle physics. And for simulation, which is the one thing I'm going to address here today, this is exactly the problem. Now, what do I mean that this is a problem? Well, say you have your favorite theory, particle physics theory, and you want to simulate events. In order to do that, whenever you're working with a real detector, which we are always doing, you need to go through a series of steps that are summarized here. So say you have a proton-proton collision at the LHC. You need to simulate the process. This process is very messy because there's a lot of QCD in there. Second acronym of the talk, I'm sorry. Then you have to simulate the showers, hadronization. This is all taken care of by the theory community. And only after you have done this and you have your decay simulated in theory, then you can add the detector effects. And then you have your simulation. So basically what this means is that this is very well separated, and I really wish it wouldn't be. Because when you look at the way theorists go about this in quantum computing, they have a very natural QUBO formulation for this. You may have seen this. Think, for example, the Higgs potential is a natural QUBO problem. Finding the ground state of a Hamiltonian. Of course, they have a lot of parameters. It's a very complex problem. Usually for lattice simulation, it means reducing the dimensions of the problem. But you get my point. So what they do is they try to approach it successfully from a Hamiltonian simulation perspective, and then at the end, they have a ground state of this Hamiltonian with all the particles according to the model. But the particles here, as I've said, they don't have any detector effects. And how, as experimentalists, as a community, have dealt with this so far? We take a very different approach. We take generative models, so it's circuit-based, and we try to train them on real data, and we we recreate the distributions that we see. So we are very agnostic in that sense. We don't make any assumptions on the physics. And then as an output, we want to get the electric deposits or the energy deposits that we see. So you can already see there's a disconnect here. Quantum that was very successfully simulated here if you do it well and you do it properly, which they do. And I put just a reference out of many here for you to see. The quantumness here is lost in translation here because it's not approached altogether. Even though it's the same thing and it's part of the same chain, it really does not go from beginning to end. It stops and then it moves forward in a different way. So we thought, why don't we try to approach this differently so that we, A, don't get the quantum lost, and B, we hopefully can integrate everything together so that we have a coherent way of simulating things. If that was not enough motivation for you, it's also a very big thing for us that simulation is really, really computationally expensive. This is the jobs that we send to our grid, and we have a lot of computer farms across the world for this, and the green is simulation only. The simulation queues, like LHC collaborations would be a much happier place if these were not so big, because people really fight over those, which also means that simulations take such a long time that they are very often the main systematic uncertainty of the measurements. So it really is getting serious. We really need to get the simulations under control. And of course, part of the reason why these simulations are not working so well with our data and are introducing so much uncertainty is because we have lost the quantumness. So we have to do corrections a posteriori, and it all seems a bit too a posteriori for what we know, because we do have the model and we could simulate it. It just hasn't been done so far this way. And then, again, it's only getting worse. We are getting more data, which is very happy news for particle physicists. We hope to discover physics beyond the standard model. But it also means that these simulations are only more complicated. You have much more proton-proton collisions happening all at once, and it's just very tricky and very challenging. So how great would it be if we can finally assess this in a coherent way? Now, I did a postdoc on track reconstruction, so I really cannot go one quantum computing talk without saying, okay, I've been complaining that experimentalists, we don't approach QUBO. We do. Only we do it in a different way. We use QUBO formulation for track reconstruction, and we do this successfully. So, of course, we are not strangers to annealing, and we do know the power of it and how to use it, but it's just, once you come to the issue of reconstructing tracks, you have already simulated your event. So it's a similar problem, but not quite. This was just one slide to entice you to track reconstruction, because this has taken 3 years of my life. Okay, so when we started trying to approach this, we had the most immediate idea was, as I've said, we can formulate event simulation with a QUBO, complicated, but a QUBO, nonetheless. What if we could do a variable transformation in the middle, and then we plug it in to the reconstruction QUBO? Variable transformation here is kind of an understatement of what really needs to happen, because if you have the truth level information, so you have your ideal particle simulated, this variable transformation would need to simulate everything that happens in the detector. And I put a detector here just so you can get an idea on how complicated this is. You have to account for the magnetic field propagation, which is not trivial. You have to take into account material interaction, multiple scattering, resolution effects, detector effects, a lot of particle physics things that are very important for precision measurements. So at first, this really seemed like the way to go. My conclusion for this slide is it could be done, but we would be, again, on square one, because I really don't think this can be done in a quantum way or an analog quantum way. I would be really happy if somebody contradicts me here, because it definitely sounds like the best way to do it, because we already have this and we already have that, and we only need the thing in the middle. But there are some stochastic effects here, some Monte Carlo things here that we really seem to prevent this from being applicable in quantum, unless you really go to very big stretches and you lose the naturalness if you try to do this. So we said, okay, so it really seems that this is not the way to go. So we had another idea, and this is the one I'm going to be focusing more here. And then you can tell me your feedback and how do you see this for quantum annealing. And here's the idea. The idea is slightly reformulating the problem such that in the QV matrix that theorists simulate, we add a matrix that sort of accounts for detector effects. Now, I will go through how to build these matrices, but of course you can already see this is not an exact formulation of the matrices. It can never be. I mean, it couldn't be before, it cannot be now, but it can get pretty correct for a lot of use cases. So, while for the initial QUBO, the theory one, you would have a wave function that you minimize in your Hamiltonian, here the variables that build your Hamiltonian, your QUBO, and your QBO formulation are an array of particles. And at the end of the day, in the ground state of this Hamiltonian, if the label of the particle is switched off, the particle is forbidden by the simulation. If it's on, it's present in the simulation. And then, as I've said, you have a matrix where you parameterize the detector response. Because, yeah, you have to simulate it every time. It's true that it changes from event to event. The detector is a very complicated thing. And we all love it because it's so messy. But you can parameterize it, and it can give you pretty good results, even if you cannot get the full answer. So one very good thing about this formula, this way to go about this problem, is that all the information would be considered at one. Very good. And then all the tracks would be directly inside the detector. Let's see how the physics Hamiltonian would look like. You would have a likelihood from your favorite model. If you don't want to go for a model, you can place kinematic constraints. This is what we call phase space Monte Carlo. It basically means kinematic cuts on the momentum of the particles and the conservation of the momentum. And then you have the quadratic term when you impose momentum conservation, angular separation, spatial requirements of your decay wherever the detector is. It doesn't matter the detector for this part. For the detector Hamiltonian, you can impose a lot of things. You can go very specific or very general. But a few important things is you should make sure that your decays fall inside the detector acceptance, and then you should make sure that particles that belong together really are together. And you can do this because we are very savvy with reconstructing the geometry of the particles. One immediate thing to consider is that I'm adding all these terms. All these terms will, of course, be coupled with Lagrangian multipliers that will not have a definite value, and in their strength lies how well your Hamiltonian does with the general decay that you want to assess. Now, I will give you one example, and of course this is not randomly chosen. This is the golden decay for my experiment, arguably the golden decay for the whole LHC, but I'm very biased. And this is a B meson, which is 2 quarks decaying to 2 muons. You don't really need a lot of information on this decay, but there are things why I have chosen this decay. I have chosen this decay because it works very well for what I wanted to present. You only have 2 tracks. So your vector of variables is really it's quite small compared to what could be in more body decays. This is a very rare decay, which means it happens 3 times every billion of B mesons that are produced. So it makes it very theoretically interesting. It makes them theory models very well developed, but it also means that it's the background you don't have to care about. So I tried building a Hamiltonian just to have a feeling of what a Hamiltonian like this would look like. I had my physics Hamiltonian. I didn't want to choose a model. You plug in a model here, can be a standard model, hopefully not. Then you build a requirement that you only have 2 muons in the final state. You want these 2 muons to point to the mass of the mother particle, in the case the B meson. And then you impose some qualities on the track. You want the track to be very displaced from from the collision point, and blah, blah. So I had a lot of fun doing this, but the main takeaway is you can do it. You just have to know your decay. You want to know how does it look in the detector, but we do have this information, so this information can be applied. I have not seen this decay, but I can already model it, and it will probably give me good results if I choose my Lagrangian multipliers wisely. Thanks. Now, where to use it? I have said that this would be a way to approach simulations, and it is still true, and it holds, and it really would be a beautiful way to deal with this, and it would save us from some simulation software in particle physics that, as a community, we really don't like very much because it's so difficult and so costly to use. It combines theory and experiment, and you can leverage the properties of quantum computing if we manage to build this formulation in the right way. But actually, as we were doing this, we realized it may actually have another application, which is in the reconstruction pipeline itself, because I was saying, oh, this is so rare. And I built my Hamiltonian that will only allow the particles I simulate to be inside the detector and be the particles I want. So if I put there where the detector makes the decision to save data, which is called the trigger, that would be fantastic. It could improve my signal-to-noise ratio. It could really simplify my life. And also, this is a combinatorial optimization problem, so quantum computing really does seem like a good alternative to what we have. If this is the detector data handling, again, for my experiment, I'm sorry, I'm very biased, you would have that it can either fit in particle simulation, taking over these three things, or in trigger, which is when it fires a decision that saves the data, because we cannot possibly save all the data. So it really has the potential to go in both places, and it would help a lot either way. Now, what do we actually need for this? We would need an analog quantum computer that has as many qubits as particles we have in this decay. A typical event at LHC has 1,000 particles, which, okay, is not impossible, but it is a lot. But then if you constrain yourself to some cases, it can really go down. For example, rare decays, Higgs decays, which are very important for particle physics, as you can imagine. LHCb is really in a good position because it has a very definite geometry, and you can place very stringent constraints. And in the field of future colliders, which would really align well with quantum computer, if we think about electron and positron colliders, muon colliders, the environment is way less messy than proton-proton because you don't have hadronization. And so it can also help there, like you can think there, the requirements are really not as big. And I put here a picture of a future muon collider, so that you see we are working on it. There has not been a decision made, but it's certainly a very good possibility. Okay, so this leads me to my takeaways. Simulation is really an essential and very expensive part for the particle physics pipeline. The approach that we take so far seems rather disjoint, and we would like it not to be. It has very good potential to be approached as a joint cubo, but again, we have to take care of the formulation and the choice of multipliers, and we really hope if we could get your feedback here. And I think that's the end of my talk. So thank you.
All right. Do we have questions? So I have some, because I know basically nothing about particle physics.
Okay.
And you wrote at some point that the muon decay results in two tracks well separated from the proton-proton collider. Yeah. Is that because the mother particle lives that long?
Yeah, because the mother particle flies along, proton-proton collide, mother particle flies, and then you have the muons which go through all the detectors, so they are very easy to reconstruct as well.
Okay. And the O of 1,000 particles from one event, event is like one proton-proton
collision.
Because all the,
because you don't have one proton-proton collision, you have several at once, so really it's messy.
Okay, and the 1,000 is like all the decay products plus their decay products and so on.
Exactly. Then you have to find your decay, which is finding a needle in a haystack, and then you have to take into account all the other processes that led you to your decay. So it's quite complex, yeah.
Yeah, I see. Thank you very much. Further questions, maybe?
So, I mean, you seem to be quite advanced already with a proposed Hamiltonian. I'm sure you have some ideas of what to put in that model. Have you played with it a bit, or?
Not yet, because I first want to see how to better find the Lagrangian multipliers, and I fell into a rabbit hole, because if you optimize the Lagrangian multipliers, it matters the physics model, and then you have to choose the physics model, and then, well, I had an existential crisis, and here we are. But no, I have not played, but I want to implement this and try to see how it behaves indeed.
Oh, yeah, right.
Yeah, so I think it would be, of course, nice to use a quantum annealer or something to solve this QBAL problem, but I was also wondering if you considered other formulations of your problem, like, because it seems to have quite a few constraints, and in a QBAL formulation, then you have to deal with all these lambda things. You could also write it as, I don't know, an ILP or some other like optimization format and use as some kind of standard solver.
A solver using a quadratic formulation as well, or a solver using a different approach?
I mean, I'm not. Yeah. I don't have anything concrete in mind, right? But I mean, one drawback of going to QBAL is that you have these kind of the constraints that you have in your optimization problem become kind of energy terms with these lambda multipliers here, and so if you would just leave the problem as a real constraint optimization problem and try to solve the constraint optimization problem directly, that may be easier.
Definitely, yeah. We can also try to do that. One thing is, maybe I was very pessimistic about the Lagrangians, but in track reconstruction, I always find a way to bring things to track reconstruction, but here we also had quite a number of Lagrangian multipliers. And I say we have to be very careful, and we have, but for this case, we also had detector effects, and we found that they can be left constant for a pretty wide number of cases. So it's something to pay attention to, but it's not too worrisome. But yeah, indeed, a constrained optimization would also be something to explore.
All right. Do we have? No? Okay. Then, let's thank Miriam once again for the nice talk.